Thanks, David, for accepting our invitation to talk here today. David is a Blavatnik and Rothschild Fellow at the University of Cambridge, working on modified gravity in astronomy at the AMPT and Kavli Institute. Before that, he finished his PhD in Ben Gurion University and spent 2 years as a visiting researcher at Frankfurt Institute for Advanced Studies. Today, he will present the dark energy in two-body problem. David, please, you can start when you're ready. Thank you.
Thank you very much, and thank you for the opportunity to speak about this topic. So, I know that usually in cosmology, if we want to measure the cosmological constant, we need to go to really far away galaxies. We need to take a look on at least type 1a supernovae, which is they're very distant from us, or to take a look on the early universe measurements from the cosmic microwave background. But today I'm going to show you some other possibilities actually to track the cosmological constant or other dark energy models. So I would say that the cosmological constant has an impact on the local universe itself, and this is what I'm going to discuss in the first part of the talk. There are other possibilities also to test dark energy models. Broader theories of gravity from binary pulsar, from the S2 star, and all of these sorts of theories. Depends, on the time and how much people still will be concentrate. So I'll try to speak, but at least to give you the impression that beyond cosmology, beyond the very large scales, it is possible actually to test or to bound the cosmological constant on very good orders, also from the local universe, or also from other binaries or binary galaxies. So first of all, this is a short review that I think all of the people here get to know. It's why do we need actually the cosmological constant, right? We have a bunch of data sets that actually showed shows the presence of the cosmological constant that caused to the expansion of the universe to be accelerated, right? So for instance, here we see the type 1a supernovae. So this is the distance modulo in different redshifts, and obviously here this is the omega mater versus and omega lambda. So, and again, if I would put the cosmological constant inside, or if I wouldn't put the cosmological constant, I would get a different expansion rate, right? So this is only matter, or if I have matter and lambda. So obviously different expansion rates emerge from different values of the cosmological constant. This is, for instance, from the type 1a supernovae, but besides this, we have a lot of measurements from the early universe, from the CMB, or from baryon acoustic oscillations from the late universe and the early universe. And there, this is mostly for power spectrum or multiples and everything. But bottom of line, if I'm adding the cosmological constant inside the gravitational equation, or if I don't add it, I would get a different power spectrum. So obviously the cosmological constant is there. But as you know, there are more theoretical problems than understanding why it has this value and everything. But bottom of line, we detect the cosmological constant from these systems. So then the question that actually emerges, if this is only the cosmological constant, or there is bigger theory that should exist. So I'm not going to discuss in the beginning about modified gravity, because I'm going to discuss about the impact of lambda in two-body problem, actually. Directly lambda. But this is another constraint that I want shortly to review, because it's really important also for the field of modified gravity. And this constraint, and it's really famous, it's really important in our field. Any theory of gravity, you have to ensure that you have this bound, that it's compatible with this bound. Just by the way, if you have any comments, any questions, please stop me and ask. This is completely fine. Feel free. So one from the constraints to have a general theories of gravity. This is what the speed of gravity and the speed of light equivalency. So we detect the Newton star measurements few years ago, and we detect also like the gamma ray burst that emerged from this event, but also the gravitational waves. Now, from these two measurements, we could observe what is like the difference in between the speed of gravity. When I'm saying the speed of gravity, I'm referring to the speed of propagation of the gravitational waves, okay? Speed of gravity and the speed of light. And apparently the constraint is like freakishly, like strong, okay? It's really strong. I mean, like 10 to the power of minus 15 to the power of minus 16, like in between zero, actually, right? So it means like they should be the same. Now, why this constraint is like so important? So one from the very general theories they try like to do in cosmology, I mean, it was like from the 70s. I mean, Hordensky invented like these combinations of theories, but it was like in 2000, like it's more and more used because, I mean, we detect lambda, and then like we needed like a general framework for other theories of gravity in order like to detect the other possibilities. And so as you can see here, this is like, let me refer to the signs that you see here. So R, this is like the Einstein term. This is the curvature, the Ricci scalar. And phi is the scalar field. In a second, I'll show that actually that dark energy could be mimicked by a scalar field. But now this is like a very general framework. And X this is the kinetic term. Okay, so phi dot square. And again, when you have like all of these combinations, you can have any possibility that you want. But then Hordensky, when he tried like to write down like his theories for the first time, he said, okay, I want like my theory to be stable and free from ghost. Free from ghost, it means that the energy density, when I write down like the density and the pressure, the density is going to be positive, not negative. And stable, it means that if I write down the corresponding Hamiltonian, I would have like Hamiltonian, which is like with a minimal point. So not like terms like, I don't know, P, Q, cube, or something like that. It's going to be unstable, okay? So with these two constraints, you try like to find the whole permutations in between scalar field and the kinetic term. So this is like the theories that they come up with. Okay, very big, and you have like a lot of constraints from cosmology. I mean, it was like a big, you can say, factory in some sense, like of papers, like how to take like cosmological data from the late universe, from the early universe. But from only this constraint, the only remains part from the Hordensky theories, this is the only green part. Why? I mean, let me give you like a bit more intuition besides like the theoretical equations that you see here. In principle, if I'm taking like the R term and I expand this like as a gravitational waves, so I requiring that I have like a flat spacetime, but over this I have like some perturbation, from the R term, I would get something that looks like a wave equation, which makes sense. But if I'm couple this to a derivative of a scalar, or I don't know, here for instance, you have like a G mu nu, which is like the Einstein tensor, and also with higher derivative and so on and so on, bottom of line, you will get some friction-like term in your wave equation. So bottom of line, you actually breaks this equivalency between the speed of gravity and the speed of light. Okay, so this is why the only part that actually remains, it was like this R, and also like multiply this by G4 phi, but without like the X. The X is also not possible anymore. But again, I mean, for the overview, because like I want to give you like the intuition here, we need to have like the speed of gravity, the speed of light, like to be the same. And this is why we cannot have like all of the permutations as we had before. Okay, so like after like this detection of gravitational waves, immediately like one day after, I mean, they have like at least 3 or 4 like physical review letters, and then like they tried like to submit it directly, like which theories are still viable, like after these constraints. And again, if there are some questions or discussion, I mean, you can stop me at any point. So why I would like to share like this Hordensky theories? Because it is possible to mimic the cosmological constant, and this is only for the sake of argument, because in a second I'm going like to discuss about the cosmological constant in two-body problem. So lambda itself, not like a general theory, but in general, it is possible to mimic the cosmological constant by more interesting dynamical field. Now, you may say, why do you need so? I mean, but on the other way around, you can ask why to have only lambda. I mean, maybe let's have like something more interesting that could be like mimic lambda. So I mean,
David, I just have a quick comment here, right? So you can do this, of course, but H0 is anti-correlated with the equation of state, the dark energy equation of state, when you fit data, right? So if you go into the quintessence regime, if W is greater than -1, you expect H0 to go south to smaller values, and all local values are sort of biased larger relative to Planck, lambda CDM, right? So, you know, I mean, if you're a theorist, this sort of tells you that it looks like you're going in the wrong direction, at least with dark energy. Do you have a comment, or would you like to address that, or?
Yes, yeah, I mean, my comment for right now, it's like to state, I mean, only the general statement, even not to like, for the sake of argument, you can have a dynamical field instead of like lambda. This is like my main statement. Obviously, there are like some constraints from that. So I totally agree with that. Okay, so I mean, in using like the quintessence model, so we have like, instead of like the lambda itself, we have like a scalar field, right? I mean, so we have like the scalar potential, but you have also like some kinetic term. Now, the equation of state of the kinetic term is actually stiff. So it means like it has an equation of state of 1. This is like the density, and this is like the pressure. And this is like equation of state of 1. And the potential, it looks like the cosmological constant. So this is like V of phi with plus and minus. So it's like the equation of state is like similar to lambda. And in that sense, I mean, if we want like to mimic dark energy, we need to have what's called the slow roll approximation. So it means that the kinetic term is partially negligible to the potential. So it means that if we have like a asymptotically flat potential, so the kinetic term is going to be very negligible, like in that asymptotically flat, we can mimic the cosmological constant. And obviously there are like some constraints or some problems also like with late universe measurements, but thank you for that comment. So my main question right now, I mean, okay, so there are some theories, there are some constraints from cosmology, very strong and very, I mean, valid. But then, is there any other possibility to detect or to give a bound on the cosmological constant or other theories of gravity in actually in binary motion or other interesting systems? So one interesting system that I'm going to discuss today is the local group of galaxies. So I wasn't like the first one like to have like this detection. I think it was Ofer Lahr, but also like some Russian researcher beforehand, a bit before Arthur Channing, they observed that actually the cosmological constant changing the whole motion of Andromeda and the Milky Way, not by a lot, but about like 10%. And it's not negligible. Okay, so I mean, we have to take this into account. And from the equations that I'm going to show you today, I'm going to give like the intuition why this is actually happens. So I did like the analytical solution is also like some simulations correspondingly in order like to bound lambda from the local group. But bottom line, you will see that we can test lambda or can give some constraints on lambda, not necessarily from cosmology. So this is like the main statement that I want like to discuss today. So in our model, and again, this is like a fairly, you know, it's not like the complete assumption you could say about lambda. I mean, obviously you need like more assumptions or more simulations in order like to give the full picture, but the local group of galaxies in some way could be seen as two-body system. So it means that you have like Milky Way and Andromeda galaxies, and you have like a lot of dwarf galaxies around like these ones. So like the dark matter halos, which actually exist, is partially negligible most of the history of the universe. Okay, there are some papers about it. Actually, there is a discussion more about it. But I mean, for the sake of argument, because I won't like to share some statement with regards to that, let's stick with this assumption. Okay, so we're taking a look like on Andromeda and the Milky Way. In certain cases, I mean, also there are some papers that are like adding like M33 as a third body or something like that, as a free body motion. But I mean, it's partially smaller than like these two galaxies. So how can we estimate the mass of the local group based on the measurement that we have from Andromeda? Okay, we can estimate the mass of the Milky Way, we can estimate the mass of Andromeda independently from the measurement of flat rotation curves and so on and so on. But there is like an argument, it's called the timing argument, that used also here a lot by Donald Lindell-Bell from the Institute of Astronomy here, that we can actually estimate the mass of the local group only based on the kinematics of the local groups. So what are the measurements? Let's give you like some overview. So this is Andromeda galaxy here on the right-hand side. The scale of the local group is about 1 megaparsec, okay? So, I mean, very close, right? I mean, so usually when we go like to type 1s supernova, it's like about 10,000 like megaparsecs and more and more and more. So very close to us. And also like the velocity is not that high. I mean, I don't have even like to go to first post-Newtonian or second post-Newtonian expansion like in gravitational waves from pulsars or whatever. There it's like first post-Newtonian. Here the velocity is very low, okay? It's 110 kilometers per second. And what is the tangential velocity of Andromeda? There are actually 3 different estimations from 3 different times because we have like new measurements. So if you go like to this reference by Van der Merwe, like 2015, they gave like upper bound of 17 kilometers per second for the tangential velocity. And later it became like bigger, about like 50. But today in Salomon et al., this is based on Gaia measurements. It was, I mean, the title of their paper was that Andromeda motion is almost circular. So it means like that the tangential velocity is around like the radial velocity magnitude. So, I mean, we have like 3 different like measurements, and these are very important for the timing argument that I'm going to show you. Okay, so I mean, I actually use like these 3 different measurements, but they give eventually 3 different masses. Any questions so far? I didn't present what is like the timing argument yet. So the timing argument like is very simple. You know the final condition, you know like the final state of Andromeda towards us, you know like the separation, you know the velocities, and you assume a very simple assumption that, again, you need like to fix it from simulations, but I mean, as the timing argument itself, it's fine, that they started in the Big Bang like 30.7 billion years ago in the same separation. Again, we have dark matter. These are 2 galaxies. They are not 2 separated bodies, but then you can do like the corresponding simulation and then like to fix the factor in between this. But for the timing argument, we assume like 2 separated bodies. They started like in the Big Bang, and then like they finish like in the certain location and velocities that we have today. Okay. So this is called the timing argument. Now we need like some equation of motion actually to describe the motion of Andromeda. Okay. So the equation of motion that we're going to use, this is like the Newtonian part. Okay, this is like gm over r square. But also we are going to include the cosmological constant contribution. In a second, you will see why. Okay. Now, so this is like the part for the angular momentum per reduced mass. This is like the total mass. And here we're taking into account also like the cosmological constant. Okay. Now, for the sake of argument, before I'll show like what is the timing argument result, because we have like the initial and the final conditions, so we can find the mass actually from that. If we assume that the mass of Andromeda and the Milky Way is about like 10 to the power of 12 solar masses, which is like known also from measurements on the galaxies themselves, and we put like here 1 megaparsec, like the order of magnitude, okay, like the size of the local group is about like 1 megaparsec. The acceleration that's coming from the Newtonian part is actually canceling the acceleration that comes from the cosmological constant part. Okay, this is a very surprising result. So, I mean, the cosmological constant itself as a force is not negligible in Andromeda motion. Any questions so far? Okay, I didn't calculate yet the mass. I just estimated like the mass. It's going to be like 10 to the power of 12 solar masses. And this, like these 2 parts, they are canceling each other. They have like the same order of magnitude. So obviously we had to take lambda into account in our analysis. Okay. So, so the timing argument is like, we know like the final condition, we know the initial condition, and then what is the actually corresponding mass that fit for this like initial and final conditions. So I did like the corresponding trick. I took like the final condition of Andromeda, and then like backwards in time, I tried to search where what is going to be like the distance at the Big Bang. This is like the plot that you see here on the left-hand side, on the right-hand side. Okay, so this is like the distance at the Big Bang. When the distance at the Big Bang is actually gives you 0, you know this is actually the prediction of the corresponding mass. Okay, this is like on the other way around, like to do it. Now, when I didn't include the cosmological constant, I got like about 4. But when I include the cosmological constant, I got about 5. Okay, the mass of the local group from the timing argument. So I mean, you see that the cosmological constant gives you like a contribution of about 10%. Now, this result, it's not my original result. This result is like in this reference by Ofer Lav and others, and Yehuda Hoffman. But what I want to like to proceed from there, there is a question?
Yes, I have a question. I mean, when you go back in time, eventually you hit the relativistic region. So your Newtonian approximation will not be valid anymore.
In which sense?
Because you are going back to towards very high energies, no? Close to the
No, because I'm searching like, I mean, backwards in time, and just like try to search, right? I mean, this is like the final location, and backwards in time, what is going to be the initial distance? And then I'm trying like to see where is like the minimal one. Oh, I mean, I know what you're referring to. So actually there is like another part, which is like really important, which is the angular momentum.
Exactly.
And this is why you have like so minimal distance. So it's not like 0, okay? So this is why it's like a minimal.
Question, yeah,
you can see that also like in the effective potential. Okay, so there is like a minimal distance here. Okay.
Okay, thank you. Yes.
Thank you for the question.
That was my point.
Thank you. So, obviously, as you see, I mean, the cosmological constant is not negligible like in these scales. Now, you see like on the right-hand side here, this is like the effective potential for the known mass of Andromeda and the Milky Way. And this is like the effective potential without the cosmological constant, but this is the effective potential in blue with the cosmological constant. So Andromeda galaxy is about here. So, I mean, if Andromeda galaxy by accident would be a bit farther away, it would actually go to infinity because of the Hubble flow. But we are very lucky that Andromeda galaxy is more or less like about like this point. Okay, so immediately what we're thinking, I mean, this is like the main, the immediate motivation or the immediate intuition that there is like some distance or some external distance that actually quantifies when the cosmological constant is important to take into account. But what I'm going to show in a second, when I solve like the two-body problem, that this is actually not an external distance, but some time, like a very important time that gives you like the importance of lambda. Okay, but this one we'll see in a second. But any questions so far? I mean, for the results, how the mass is like changed from adding lambda? Any questions so far? Okay. So in order actually to solve the two-body problem, let me try to, I will try now to go to share here, because I think it's going to be like a bit more intuitive. I'm going like to show in a second, like roughly what is going to give you. So let's assume that you have like, you know, like elliptical motion, okay? And so the Newtonian equation, it's like minus gm over r square, okay? So usually we can solve like this equation. I mean, we know like the solution for two-body problem for this equation, I mean, by assuming like the spherical coordinates and so on and so on. But usually there is like what's called the mean anomaly parametrization. What is like the mean anomaly parametrization? What is like so important? So if I'm surrounding the whole circle by another angle, this is like the true anomaly, theta. And this is what I'm calling like the mean anomaly. So it's like another angle that actually surrounds the whole motion that I have. Okay, so let's put it like, and then I can parameterize my solution. So R equals A E cosine eta. This is like some parameterization. And then I can take like this parameterization inside the energy. So like if you recall, the energy is like half V square minus GM over R square. And then I can take like this parameterization inside here, like inside my differential equation. After like a bit some time, I can get like a very elegant solution. So it's going to be like NT, and this is the period, equals to eta minus E sine eta. Why this parameterization is so important? Because it connects for me the time into the separation by analytical term. So this is why it was important to me like to parameterize like this solution. So now let's go back. I mean, let me only show you. This was only for the sake of argument. So this is like the known two-body problem solution for the Newtonian potential. But here if you introduce like this parameterization of eta, you can have a connection to the time. Okay, this is only like it's very known like in the courses. So okay, but this is like gives you like a simpler solution. Any questions so far? I'm not going to use like the equation so much, but now the same thing it is possible to do. Oh, happened. Okay. The same thing it is possible to do for the first post-Newtonian as an example. So I mean, like in the first post-Newtonian, as you can see, you have like the equations for R dot and theta dot. The theta, this is like a true anomaly. And you have some higher orders for the polynomial because of like the first post-Newtonian expansion. So I mean, because of like GR contribution, you get like some additional terms. But bottom of line, this is why I want to show why I use like this parameterization. It's like very important. The two equations that you saw before that describes for you like the whole motion, it's only changing to these two equations. So now you define like a temporal eccentricity, okay? Instead of like the regular eccentricity. Now, why this is actually important? Because if you run a simulation that you have like for different times, what is going to be the separation, you get immediately the precession that we know from GR. So again, like these two simple equations, which are analytical equations, gives you the full motion for the first post-Newtonian expansion. Okay, this is like why this is like very important. I'm not going to like into details. Any questions so far? Okay. Now I wanted like to do the same thing for the cosmological constant. I mean, so to get some intuition why the cosmological constant is actually important in the local group. So when I started like to do the equations, I got like some dimensionless parameter that emerge from the equations all the time. So like it's going to give like the next order contribution. And this dimensionless parameter, it was lambda multiplying by these parameters. Now, M is the total mass of the local group, and A is the semi-major axis, okay? And GM over A cube, if you recall, this is actually the Keplerian orbit. And lambda is 1 over length squared. I mean, more or less like the horizon of the universe, like the size of the horizon of the universe. But lambda c square is actually some time, is actually some period, which is about 63 gigayears. So the condition that I got here, it was like the Keplerian orbit over 60 gigayears. This is like the dimensionless parameter that quantifies for you the modifications if you have the cosmological constant in two-body problem. Now, the Keplerian orbit of Milky Way and Andromeda, if we assume they started like in the same location and they finished here, they are going to finish like in a few billion years. The Keplerian orbit is about 20. So 20 over 60 is a third, okay? So this is why the cosmological constant is actually gives a perturbation for the over the Newtonian force, okay? There are any questions about like this statement? Okay. So as you can see, this is like the analytical term that I got before for the Newtonian one, but then this is like the modification, the first order modification. But again, I mean, now you can know for sure what is the general condition when the cosmological constant is going to be non-negligible in two-body system. If you have like two galaxies, two binary galaxies, I mean, you can take like a general one. They have a period which is about like the age of the universe or more. The cosmological constant is going to affect the whole motion. Okay, so this is like a general statement for all of these systems. So when I try like to do like as a prior, we know like the separation, the radial velocity, the tangential velocity, the cosmological constant, the age of the universe, and then like to get from this what is going to be the semi-major axis, eccentricity, and so on and so on. Eventually, from the MCMC, I got like the value for this small lambda, this dimensionless parameter, which is about 0.1. So again, as you see, this is like the theoretical explanation, and these are like the numbers. The 10% is actually because of this fit. Okay, so this is like about 10% contribution for the whole motion, actually. But now, so we had like two different papers. I mean, now the first one is about like the latest estimation of the mass of the Milky and Andromeda galaxies. Is there any question here, I think? Or?
Yeah, I have one question. Like this small lambda and capital lambda, these two are related, I mean, with the cosmological constant?
Yes,
okay,
so
here.
Here, so you see like it's like big lambda, but then you have to multiply by some factor inside. Okay, but I mean, yeah, and I mean, by the way, I mean, if you want like to see where this is this dimensionless lambda is coming from, I mean, I can give like more intuition, even more than this. Okay.
Yeah.
So minus gm over r square. This is like the Newtonian part. Lambda c square r. This is the cosmological constant part.
Yes.
So let's put the ratio between these two. So lambda c square r over gm over r square. This is actually small lambda. But now instead of r, put the semi-major axis.
Yeah.
But the surprising, yes.
Yeah,
and
thank you.
But the surprising thing is that actually this parameter appears like in the two-body solution all the time.
Yeah.
Thank you. Okay. Okay. Let's go forward. Yes. So in the first paper, me in a collaboration with Ann Davis and Wynne Evans and some collaborators from the States, because they had also like the full simulations of the Milky and Andromeda, and Eugene Vasiliev, we tried like to give like the latest estimation for the mass of the Milky and Andromeda galaxies, and we included the cosmological constant. I mean, you can see like the paper in the archive, we had the contribution of lambda there. But what we observed, I mean, this is one some observation I had like even before my starting like my fellowship in Cambridge, that actually higher tangential velocity giving like higher masses for the local group, predicts higher mass for the local group. Now it pretty makes sense because you know like the final condition, and you know that there is like some Newtonian force that attract the galaxies, but then the tangential velocity is like trying like to cause them to run away. But then if like the VT is like larger, you need to have like larger mass in order like to finish in the same final condition, with the same separation, the same VR, and so on and so on. So this is like, again, like the trick that I've done, like to take backwards in time. But then you see that when I put like a different tangential velocity, I got like different prediction for the masses. Now, again, this is without taking into account the correction from simulation. So, I mean, even like the mass is like very high. I mean, 6×10 to the power of 12 solar mass is like really huge. You have to take some factor into account that modifies like this timing argument. This factor, we call this the cosmic bias. So we took like a lot of like simulations of like of Milky and Andromeda type binaries, And from the parameter space there, we try like to find where like the best point, which actually corresponds like to the timing argument. So, and this is how we found like the correction factor. So this correction factor eventually it becomes like about 0.63. Okay. So bottom of line, with the latest estimation also for the tangential velocity, because this is actually predicts higher mass, and with the correction factor or other galaxies that also Eugene tried to add like in the simulations, we got like the latest estimation for the local group, or for the mass of the local group, which is about 3 10 to the power 12 solar masses. Okay, so, and this was like published like last year in Epigene Letters. But I mean, the surprising thing, and I think that there are some papers that agree with this, there are some papers that disagree. So I mean, this is like some open for discussion in some sense, I would say, that you see that the total mass of the local group is actually the masses of Andromeda and the Milky Way. So I mean, like there is, most probably there is like some halo of dark matter around, but it's not that dominate as like the masses themselves around the galaxies. Okay, and actually I think like short time after, I mean, it was like some paper that the title of the paper was no more than the masses of this galaxy, something like that, and cited like this reference as an example. Any questions so far? Okay, I'll skip about like this statement. Now,
There is a question.
Yeah, please.
I have the following question about the mass. What do we mean for mass? If we consider, you talk about modified gravity, but if we consider higher derivative gravities, for instance, or in r plus r squared, the mass, the Keplerian mass, does not coincide with the ADN mass. That's a known result. And
I'm trying just to understand your question, because I didn't include here any modified gravity. I mean, lambda is there, right? I mean, so
that's purely Newtonian. There is, but eventually then there is something that you will have to face to define this mass. So your mass is the Keplerian mass, Newtonian mass, it's the standard. It will be exactly that. Right. Not the quasi-local mass, nothing like that.
Right.
Okay.
Yes. No. So I mean, this is a very good point. If you have like other theory of gravity, you would get like different predictions for the mass, definitely. But because we know the masses also from Milky Way and Andromeda measurements, or like independent, estimations, you can give constraints on modified gravity only from the local group dynamics. This one I'll show like in a second, but that's correct. So how can we actually bound lambda? Okay, I mean, it's like to do on the other way around in some sense. So have you seen the cosmological constant on these scales is give you like some linear force correction, like force which has like a linear dependence. Now I did like the other exercise. Let's say that I don't know lambda. I never detected like a Planck or something like that. I don't know about like the cosmological constant. But then I'm asking myself, if there is like some linear force that actually modifies the Newtonian force in the Milky Way and Andromeda galaxies, how much this lambda could be, or how much like this linear correction could be, that still it's coincide with the known knowledge that we have on the masses of the local group. Okay, so in this plot, what you can see, this is like the predicted mass with the simulations inside and everything, but then for different values of lambda. And this is fully numerical. It's not like as a perturbation theory or something like that. So, I mean, as you can see, this is like the value for 1. But I mean, if you get like higher values of linear force, you have to have larger mass. I mean, and this is pretty trivial. This is pretty intuitive. Why? Because the cosmological constant or this like linear force is actually a repulsion one. And then you need like higher mass actually to attract like these galaxies in order like to finish in the same separation. Okay. So this is why you need like higher mass when you have like higher lambda. But because we estimated the mass, or we know that actually this mass is like the sum of the galaxies more or less, we can actually give a bound on this linear correction. Okay. So when I run like the full MCMC with all of this analysis, we define like the chi-square from the known mass. So we got like this bound on lambda. Now, why this bound? Oh, sorry. So why this bound on lambda is like very interesting, because in one side, to have one, which is like the value from Planck, it coincides, but also you get like some upper bound. Okay, if you take like the mean plus the variance, it's going to be like about 9 times the value from Planck. But that's a limit which is independent from Planck measurements. So I couldn't have too large lambda, because then like the mass of Milky and Andromeda is going to be like, does it make sense? So this is why we get like some upper bound on the cosmological constant only from the local universe. Any questions so far? Now, we try like to see if actually with future measurements, we're going to have like maybe better upper bounds or better estimations. Okay, so these are like the errors that we know from the measurements that we have, for instance, like for the separation, for the radial velocity, and from the tangential velocity. The largest one is like from the tangential velocity. And then I try like to simulate like the same trick, but if I'm going to have like smaller error for the tangential velocity or smaller error for the mass. And then you see, I mean, how the upper bound is actually reducing to 5 or 4, something like that, the value from Planck, again, only from the local universe. And we estimated like, let's say that we have like only 5% error or something like that. This is like a very special case, we call this. And then the best estimation that we got, it was like about 2.5, the value from Planck. Okay, so this is like the best, I mean, future forecast, I mean, we can have ever add like in this measurement. But first of all, this is only from the local universe. I mean, also other binaries could give like a very good bound on lambda in that sense. I mean, if we will have like the same dimensions. But then this is like an open question that I would like to give you as, you know, inspiration for further research or something like that. I know that I actually gave some bound or linear force based on the knowledge of the local group. But do I really measure lambda? I don't know. Okay, so I mean, because like from this measurement, lambda could be even 0 and it could be 1. But it's not like that I got like 1 and then like some error, which is like, you know, give like a repulsion for 0, and it gave like some upper bound, but it could be coincide with 0 in some sense. Now, definitely from cosmology, we have a measurement of lambda, no doubt, and with a very high precision. But what I'm saying that, who knows? I mean, maybe in very small scales, when I'm saying very, like not in the cosmological scales, lambda could behave differently. So this like experimenting that I've done here is actually not ruling this opportunity, this option out. Maybe it's only like a very boring cosmological constant, but maybe on really smaller scales, it behaves differently in spherical symmetric solution. Okay, so I mean, the possibility from the known distributions is actually there. Any questions or comments or? Okay, so it is possible also like to constrain other models of gravity. I mean, so for instance, like this reference with Cappucciello, we tried like to take some f of r gravity models, which if you go to the low energy limit, you end up with Yokawa type potential, okay? And again, I mean, you see here like the dependence of the mass on different parameters. So it gives you sometimes like higher mass or lower mass. And based on the same technique, you can give like some bound on the Yokawa type potential. Okay, so I mean, this is like a very nice trick, but bottom of line, I mean, you can constrain lambda. You can constrain also alternative theories of gravity based on the local group dynamics. This is like the main statement that I want to give here. Okay. Just a question, Eleonora, I mean, how much time do I left? And maybe this is like the best point to stop here, or to discuss about something else a bit, or I mean, what do you think? Or
I think you have another 5 minutes, considering that you have already.
5 minutes.
Yeah.
Okay. So maybe I will just summarize. I will say like something short about it. This is like this is some paper that I published with my PhD supervisor, like doing my PhD. So these two values, like minus gm over r square and lambda r square, not they are only like in the same range as you can see here. These are like the values, but they're both also in the on the Mondian regime, where like the acceleration of Mond is expected to be detected. So like 10 to the power of 10 to the power of minus 10 meter per second square. So I mean, Mond, as you know, this is like an alternative for dark matter for galaxies. But here you have like an experiment, like how to test Mond in 2 different galaxies, like a 2-body problem. So in this experiment, we try like to find like the mass. This is like with lambda, without lambda. But here, this is with Mond model inside. And then we got like some much lower masses. But then we did like this, the corresponding claim. If we have the timing argument plus the simulations, we should get the mass that include the dark matter inside. But if we are going to introduce Mond, we're going to get the mass only for the baryonic matter, if Mond is like a good estimation. And then from the ratio between the Mondian mass and the timing argument mass, we can actually find the ratio between dark matter and baryonic matter. So this number could give like an independent test if like the ratio, because the ratio in many galaxies is known. I mean, in our universe, the ratio in between dark matter and baryonic matter is about 6. In many other galaxies, it could be even 100, but on average, it should be like 6. So from this experiment, we got that the ratio between the baryonic mass and the total mass and the dark matter mass is about like 10. So, I mean, this is like a number that with measurements, you can actually test. So, I mean, we actually show that also with the local group, you can test like different Mondian moments. Okay. So this is like the amount of like the Newtonian versus like Mond moment. So I did like more general stuff as well, like how to test different modified gravity. So I solved it like in 2-body problem, and then like with the measurement from the S2 star and from pulsars, it's like, again, it's like many theories of gravity, how to test this like in 2-body, but it's like a topic by itself, I would say. But my statement that I would love like to give you as additional, you know, like some inspiration, like to think beyond the cosmological constant. Usually we think about like size, right? I mean, like the size of the horizon or something like that. But in my calculations, is actually like in 2-body problem is actually some time, some period, 63 gigayears. So the Keplerian time over like this one, it's like a dimensionless parameter that you can test for binary galaxies, any general binary galaxies, to see if the cosmological constant is affecting like their motion. So it is possible like to use the local group, but also like other binary galaxies. This is like some things that I'm trying like to do now. How to test the cosmological constant independently from cosmology in binary motion. So beyond cosmology, we have like many other possibilities. I wouldn't say many, but there are some other possibilities to test lambda. And obviously for 2-body problem, I mean, if you're going like to dark energy models, we have like a lot of systems. So I didn't like discuss this one, but I mean, this could be like maybe an independent talk or something like that. But this is like the statement that I would love to give you as an inspiration. So thank you very much.
Thank you. Thanks a lot for the very interesting talk. Okay, so I think there is already a question in the chat.
There is like one question I see here.
Yeah, maybe, Wayne, do you want to say this?
Yeah, so let me discuss about like this question. It's a very good question. Let me read the question if possible. I think it is known that lambda can be neglected. Okay, can be neglected for the solar system in GR. Why does lambda give some measurable effect in galaxies two-body problem? So excellent question. I mean, this is exactly the condition that I performed. This dimensionless parameter, 1 second, sorry. We see, oh, what happens here? Oh. Okay, so this dimensionless parameter, it quantifies the contribution of lambda in two-body problem. Okay, so this one. So when the period of two bodies is about like the age of the universe or more, the cosmological constant is going to affect on this system. This is my statement. And because of like the solar system, all of the period of the stars is like about years and not giga years, okay? So the effect of lambda is like really negligible. Okay, so this is my my answer for that question. Please, I see more questions.
Thank you. And Erwin?
Oh, yeah, thanks, David, for the nice talk. I had a more comment, like, I guess in your forecasting, you'd like to show that basically lambda actually exists, right? You'd like to sort of say it exists at 2 sigma or 3 sigma, more than give a, it's not that you want to really give an upper bound on it. You want to prove that it's there, right? So that's the comment. And the second one is more of a question. Like, if you move from lambda to WCDM, could you say about which direction it prefers? Does it prefer to move to W greater than -1 or, you know, the phantom regime?
So this is very, I mean, this is something that I thought myself. I mean, how to take, you know, like W parameters, like the WWA, and how this is possible actually to give constraint on these parameters. But the problem, I mean, not from what I know, there isn't like spherical symmetric solution for these models. So I mean, I gave like some bound on a modified gravity parameter, like the Newtonian constant. It's going to be like some 10 to the power of -1 bound over like the running Newtonian constant. But we need like some formulation. I mean, maybe there is in the literature I didn't found some formulation how lambda or how this dynamical lambda, like W, right, is going to be appear in the two-body problem. And then I could actually run like the same simulation, then like you give some answer. So.
Okay, thank you. Thomas?
Yes. Well, first I'd like to thank you, David, for your really exciting talk. And then it inspires the following question. I feel that the cosmological constant is polarizing the community into 2 parts. One thinks that lambda is as precious a constant as Newton's constant. Both are coming from invariants of Riemannian geometry. And the other side thinks that the cosmological constant is sick and must be, that sickness must be cured by something that is called dark energy. May I ask you on if you have taken a side?
So I like in the paper that we submitted, we tried only like to test the dynamical G, and I said it was about like 10 to the power of -1, like upper bound. I didn't try like to take other theories of gravity in that sense. I mean, like FO variance as an experiment, I performed like one possibility. The problem, I mean, from the local group, we're trying like to infer the mass. So I mean, you have like one value, right? The mass of the local group, and you insert inside the initial conditions and the value of lambda. So you can usually, you can actually extract only one value. So I mean, one additional parameter. So it's still like, in that sense, it's still like lacking for, you know, if you want like to have much more parameters, we need maybe other system that we can have like more data or something like that. Because here you have like one posterior, I mean, like the mass itself. So you can use it as a prior. Okay. So.
Yes. If you think that the cosmological constant is not there and it is dark energy, of course, there are many forms of dark energy.
Right.
could you repeat your analysis,
Yeah.
which then has more parameters using dark energy instead of the cosmological constant?
It would be more complicated, because the question, how many parameters? Because here in my prior, I have like the mass, I have the cosmological, I didn't have the cosmological constant. So I have like the mass and I have the initial conditions. Okay. And from that, I try like to infer how much is like dark energy, lambda. So, I mean, so you had like one parameter that you can infer from this analysis. So if you have like dark energy, the question, how many parameters you put inside, and then which priors you put on these parameters independently. Okay, because you can infer like one parameter eventually. So this is like, I mean, this method it like has some problem in that sense. So, and also you need to solve the dark energy solution. I mean, it's not like just like a cosmological solution. It's like the dark energy model solution in spherical symmetric solution. So how it should looks like, or how, which force it needs like to give as a contribution for the Newtonian force. And over this one, you can run like the same analysis. Okay.
Well, let me ask the question in a more radical way. Dark energy, in a sense, has an infinite number of parameters.
Right.
Even
So,
in cosmology, there is an equation. Well, let's say if you want to go to away from maximal symmetry postulated in the cosmological principle, then of course you want to ask the question: what is the generalization of dark energy, which is defined only in the context of the cosmological principle, if you want to see what happens in a spherically symmetric static setting? And
yes. So if such a form exists, I mean, you could give, I mean, you could say that if, for instance, like dark energy, these dark energy models, they are like have too large parameters or too low, the masses are going to be like too different. And therefore you can give constraints like on these parameters. But it's not that strong as cosmology, because you have like a lot of like errors in the measurements of the initial and the final conditions. So it's like, I mean, it's not that good as cosmology in that sense, if this is clear what I'm saying.
okay, well,
Okay.
Thank you again.
Thank you.
Tada.
Thank you.
Alan?
Thanks for the interesting talk. You looked at one source of error on the masses coming from the errors in the measurements of the velocities, but another source of error is that it's not strictly a two-body problem. And I mean, looking at some of the other studies, such as the simulation-based inference method of Lemos et al., where they basically chose systems that look like the Milky Way plus M31. From memory, I think the variability that came from all the stuff that's around the two was similar to the sort of errors that you get from the velocities. So I wondered if we're actually at the point where there is a sort of flaw to what we can learn about lambda because of that variability, and we're already at that point.
Thank you for the question. I mean, it's a very important comment. So, I mean, this is what I called the cosmic bias. So, I mean, like I used the simulations. They include also like some dark matter, halos or additional galaxies inside. And then I try like to find the correction. So you have like the timing argument mass, but then the link to the correct mass from the simulations. Okay. So in that sense, I use like this correction, but bottom of line, even if you use like this simulation, and this is like this plot shows that if the cosmological constant is too large, the predicted mass is going to be too large. And this is why it is possible still like to give some upper bound for this linear force. But definitely you're right that, I mean, this is like, I would say a debate. Is this really a two-body problem? I mean, maybe there is like some flaw inside, and then it's needed like to be taken into account. Absolutely right.
Thank you.
Thank you. There is one question in the chat I see, what do you think about constraining dark energy models of modified theories of gravity using two-body problem of black hole binaries? So I would say in short, because I didn't discuss like pulsars, pulsars like different system, but so bottom of line, I mean, the energy scale is going to be different, obviously. Okay, so the time scale is going to be much lower. So you cannot detect lambda in these systems, but you can give very good constraints on these parameters. I mean, much better even than the local group, I would say, because you have much more data as well. I did a few things about binary pulsars, okay, not like binary black holes. In binary pulsars, I mean, you get what's called the post-Keplerian parameters. So it means like what is the energy loss, what is like the changing the period of time, right? I mean, all of these post-Keplerian parameters, and they are measured from pulsars very, very good or very well. So we can use this like to constrain dark energy models. Okay. So for instance, I mean, just let me show you here. These are like different post-Keplerian parameters. It's like a topic by itself, but and all of these parameters, this is like the precession. The first one is the precession rate. And the last one is like the loss of radiation. And we know how to measure this from binary pulsars very well. So this is why to get constraint on these parameters for modified gravity, it's a known technique. I mean, it is possible strongly. On binary black holes, I mean, I guess as well, but there you have to calculate the whole wave function that you get from the gravitational waves. So it's a bit more difficult, but it's possible. Thank you if this is like answering.
Thank you. Yes, and I think we have another question, Lakshmi Priya.
Hello. Yeah, like in one slide, you have some modified theories of gravity, for instance, F of R gravity, and you did the analysis by considering modified theories of gravity plus the cosmological constant term. And in the other way around, you did the analysis in only considering the cosmological constant term for the two bodies problem. But I didn't understand clearly, like what is the difference when you are adding the modified theories of gravity with the cosmological constant term, or only considering the modified theories of gravity without adding the cosmological constant term.
So, I mean, alternative theories of gravity, the question, which theories you are referring to? Okay, so, I mean, they give like different predictions. I mean, a lot of predictions. So, like in this paper, I mean, originally it was developed by Salvatore Cappucciello, but I think this is like, it's not like in the literature, but I mean, he derived it like in a very nice way, in my opinion. So, he showed that, for instance, if you take like F of R gravity, in the low energy limit, you get like your Kawai potential. Okay, so in that sense, you don't have like Newtonian, but you have like Yukawa. And again, like this alpha and lambda, they are related like to these parameters from F of R. So I cannot constrain alternative theories of gravity by this technique, I mean, widely. But still, if you get like some parameters that should emerge like in the Newtonian part, I mean, in the low energy limit, so you get like some Newtonian plus some corrections, you can definitely constrain or to give some possibilities, because the mass of the local group is going to be too low or too large, which not coincide with what we know. So in that sense, I mean, this is like the method. So this is possible, and yeah, this is what we have done so far.
Also, there is one slide you have some diagram between the difference between the modified Newtonian dynamics and the cosmological constant. Like, what is the difference in between these two? I didn't understand.
Yeah, so I mean, like it was like a nice experiment,
yes,
like to show that Mond. I mean, if you believe in Mond, for the sake of argument, if you believe that actually there is no dark matter, but it should be like some modified gravity, the mass that you need to get from this experiment is going to give you only the baryonic mass, because Mond doesn't believe in dark matter. It's like replacing dark matter. But then, because you have like the Mondian mass, I mean, like the baryonic mass for Mond, and you have like the total mass, which include the dark matter inside from the regular Newtonian plus lambda, you can actually find from the Mond prediction what is going to be the ratio between the baryonic mass and the dark matter. Okay, and from this experiment we got like about 10. So like the prediction of the regular Mond models from the local group is going to be like the ratio of 10. So this number can be tested. Okay, so it's like another test for Mond theories. This is like the main statement.
But also in modified theories of gravity, we are how we predict the acceleration expansion of the universe. If we say that our universe is accelerating, that means there exists some dark matter, right? We cannot say that the dark matter is not exist in modified theories of gravity.
It depends which theory you are referring to, because there is like a big ocean of many theories. So I mean, when you say modified gravity, the question what you're referring to, if you're referring to replace dark matter, or in addition to dark matter and lambda, to have some other possibility. So there are studies in that direction and in that direction. Okay, so in this test, we actually wanted like to show that if you're claiming that the modified gravity is like replacing dark matter, you can have a statement. You can have like a test, a direct test from the timing argument.
Mm-hmm. Okay, thank you for your clarification.
Okay, thanks a lot. Do we have any other questions for David?
Actually, I have a question related. It's related to the comment earlier. Like, you could just rewrite this all in terms of constraints on H0, right? So Brent Tully and cosmic flows, what they're doing is basically, you know, it's the local universe, maybe out to 200 megaparsecs, you know, at much larger scales. You really are insensitive to, you know, dark energy. You're insensitive to omega m. The only thing you're sensitive to is basically H0. So this should all be just constraints on H0 in some sense. And then, you know, obviously then you can look at the age of the universe. Now, even if you found that lambda was 0 in your analysis, I don't think there's a contradiction there. It's just that we're looking at things at different scales.
Yeah, I mean, if you are asked my opinion, yes, I mean, so even let's say that we found that lambda is 0. So it's actually saying that in really small scales, because I mean, we detect lambda for all of the cosmological analysis, but in maybe much smaller scales, we have like a different function. This is what I would say. Okay,
or it's just not relevant. It's just not relevant. The only thing that's relevant is H0.
No, if lambda has the same value, okay, so it should be relevant also like in the two-body problem. Okay, so it has an effect. It has like some 10% effect in the local group.
Right,
in
but
all the binary as well.
it's not clear to me that that lambda is the same lambda that appears in the, you know, in lambda CDM, right?
I don't know.
Yeah, that's I
a
think
very good question.
the only point, right? It's not clear that these things are the same.
It's not
Okay.
clear. I mean, if you're saying this is actually the cosmological constant, and then you solve the spherical symmetric solution for that, this is like the same, but who knows? I mean, I agree.
Okay.
Okay, thank you.
Thank you.